Yeah, so I'm going to talk to you about yet another dictionary in combinatorial algebraic geometry. So I'm a nerd and I like bridges. So let me draw you a bridge here. But a bridge is sort of useless unless it's connecting two different things. And so in our case, the two things that we're going to be talking about and connecting are quiver representations and positroid varieties. But this is a little bit broad for us, is a little bit too much. And so let's add some qualifiers. Specifically, I'm going to be telling you about a connection between type A bipartite quiver representations and positroid varieties in a particular open patch of the Grassmannian. For my intents and purposes, positroid varieties, if you want to talk about those, it's enough to talk about bounded affine permutations. And really, these are something called juggling patterns, and juggling patterns sound way cooler anyways. So that's what we're going to be connecting to today. Awesome. So now that we've met our characters, let's get to know them a bit better. And we'll start with the quiver representations. To figure out what that is, though, we first need to figure out what a quiver is. And so, so let's add some adjectives. So if we want to talk about a mathematical quiver, it's just a directed graph. Now, you can add a lot of stipulations on this, but this is already way too complicated for me. This is too hard. I don't want to talk about this. I want to talk about something simpler. So we're going to talk about type A quivers, which are the type A is referring to the fact that the underlying graph is of Lie type A, so this is all in a line with no branches. Now, thanks to a result by Kinzer and Rajkot, if you are thinking about an arbitrarily oriented type A quiver, it's actually sufficient to think about a bipartite type A quiver, which just means that each of the nodes are either a sink or a source, so all of the arrows are going into it or coming out of it. And so that means these two red arrows here are wrong, so let's fix that. There we go. So we've got our type A bipartite quiver. All right, so now let's think about how to make this into a representation. So here's our quiver. And if we're thinking about representation theory, we want to get to linear maps or matrices. And so we first need to get to some vector spaces. So the vector spaces that we're going to be dealing with are at the nodes. We're going to put some vector spaces there. And as we all know, the only interesting thing about a vector space is its dimension. And so we're going to store all those dimensions inside this dimension vector D. Now that we've got our vector spaces, we've got their dimensions, you're not going to be surprised that these arrows are actually going to be our matrices, our linear maps. So here they are. Let's think about this in an example so that we know what we're talking about. So here is a type A bipartite quiver representation with 4 vertices. With dimension vector 1, 2, 2, 1. And I've already drawn in our linear maps for us, these matrices here. Now we're going to put onto this guy a little combinatorial gadget called a lacing diagram. And a lacing diagram is a sequence of columns of dots, 1 column for each of the vertices. And in each column, the number of dots corresponds to the dimension of the vector space. Now, in order to store the data of the matrices, we're going to draw some arrows. And to see how I drew these arrows, I'm going to draw your attention to, to the first matrix here, which is connecting x1 to y0. You'll notice that it has a 1 in row 2 and column 1, which means that we draw an arrow between the second dot of x1 from the top all the way to the first dot of y0 from the top. And we fill this out for the rest of the columns of dots, and we have our lacing diagram. Cool. So we now have an idea of what a quiver representation is. We have a tool to use later, which is our lacing diagram. Let's move on. So here's a juggling pattern. So if you've ever juggled balls, you know that you're catching a ball and then you're going to throw a ball. And so we're representing our times that we're catching and throwing in the diagram by a sequence, these sequences of dots here. And then if we've caught a ball and we've thrown it, so we caught it at time I and we've thrown it to time j, so we're going to catch it again at time j. We're going to draw an arc between dot I and dot j. So this is a diagrammatic way of drawing our juggling pattern. Very cool. You may notice that this is essentially a way of permuting an infinite set, a countably infinite set, or the integers. And we're doing it in such a way that we're not sending things too far ahead, so it's bounded. And it's also going to be periodic in this case. And for our example here, this juggling pattern is 6 periodic. So every 6 dots, it's going to repeat itself. Okay, so with a regular permutation, an element of Sn, we often like to associate to it a matrix. And we're going to do the same thing here. So let's draw a matrix for ourselves. First, we're going to label each of our dots. And then in order to get the size of our matrix, the number of rows is the period of the juggling pattern, and the number of columns is twice the period of the juggling pattern. And then in order to populate our matrix, every time we're going to put a 1 in element or an entry ij, so in row I and column j, if we throw a ball at time I and catch it at time j. So here is the permutation matrix for this juggling pattern. Okay, very cool, but I promised you a connection to these quiver representations. So let's bring back that lacing diagram from before. And I'm going to tell you the punchline is that this matrix is in fact counting two things on the lacing diagram. It's counting the connected components of the lacing diagram, so these laces, but it's also counting the arrows in between each of the adjacent columns of the lacing diagram. And to see how that works, we're first going to outline some block structure onto our matrix. These blocks are, the dimensions of these blocks is given by the dimensions of the vector spaces. So you'll recall that x2 had dimension 1, x1 had dimension 2, and so on. And then if we want to actually see how it's counting, let's take a look at this lace that's going between x2 and y0. We see that there's a single lace. And so if we go over to our permutation matrix and we look at block x2, y0, we'll see there's a single 1. If we wanted to count the number of arrows between adjacent columns, so let's take a look at an example here. Let's say we're counting the number of arrows between x1 and y1. You'll see there's 2 arrows. And so if we go over to block x1, y1, you'll see there's 2 1s. This machinery generalizes, and we use that generalization in order to actually give us our connection between the type A bipartite quiver representations or quiver loci and positoroid varieties in a particular open patch of the cross-Milesian. Thanks.